Where are you in the line? There. Well, we get to see if you're better rank research 400.
Oh, Grant, are you in?
No, I was here to listen, but planning to bail. Yeah.
We have the laptop here.
Well, I still, I didn't shower.
Sorry, the present I was supposed to them, right?
But it might block the camera.
Because okay, we can here. I think that might be from this one.
Wow.
Yes, but let me check.
Video.
The presenter can use a clicker. They can use a clicker if no, actually, well, right, yeah, they. I think so. I think he probably has it at the back.
1, 2, 3.
Yeah, I think she just went to the restroom. That's what he used for.
So I may remember, I think you have 12 minutes to presentation, 10 minutes for questions.
Okay. We remind.
I will remind you when 2 minutes. Okay. So after 10 minutes, again.
My wife likes me, God, no one will do this.
Oh. Yes, Serena, and 30. Yes.
Yeah. Oh, okay, so I only looked on the floor. And with the other than.
And the slides are.
You're trying to tell what I said. You're trying to tell about this, just like, yeah. Well, I gotta wake up feeling rested. You said you full. Only 2 days ago. Also, the sunsets, I heard that too.
Where's the first starting?
Oh, yeah, sunset is. Okay, 5 and.
Just to check,
So basically. Oh, you were gonna go.
I just want to see if they're.
Yeah.
Oh, yeah. So that, yeah.
Oh. What's your like number?
I'm the third.
Okay.
Oh, that's it, okay.
Yeah, but we're missing the fourth speaker. No.
Yeah, if you can only wake up, you always. Yeah, that's like. But this is. Yeah, try. They're all very different folks. Yeah, it's. One of the. So I. Yeah, I hope, I have it in time when I will sleep over the way. We'll use my whole health and make the plan. Both of these flights, my flight here, I think it's like 6:30 in the morning, but flight home gets in 7 in the morning. Worst time will arrive. Stay waiting. Best to do all that at time.
All right, good afternoon, everyone. Welcome to this session about data, incentives, and applications. My name is Gianluca De Martini from the University of Queensland, and I'm chairing this session. We have 5 papers, so please, each presenter, keep your presentation to 12 minutes, and then we have 3 minutes for questions, and then we switch to the next presenter. The first paper in the session is titled Mitigating the Participation Bias by Balancing Extreme Ratings. Will be presented by Jialiang Liu. Thanks.
Good afternoon, everyone. My name is Jialiang Liu, and I'm glad to introduce our work mitigating the participation bias by balancing extreme ratings. My co-authors are Yunkang Guo and Yuqing Kong. We are from Peking University. So there will be 4 parts. I'll talk about the motivation, our simple model, the main results, 2 aggregators we propose to aggregate the ratings under participation bias, and finally some techniques if time permits. The rating aggregation plays a crucial role in many fields, such as movie reviews, teaching evaluation, and hotel rankings, and so on. I believe most of us has a experience of rating some item on the online platform, or at least invited to do so. So this is the real experience of my co-author Yuqing Kong. She was invited to complete a survey after her stay at the hotel. Usually she would just ignore this kind of emails, but this time her experience was so bad that she felt compelled to leave a negative review. So this is her review. She rated 1, slightly better than 0. So now you know why I hide the name of the hotel. Anyway, you can see raters with different experience may have different participation probability. Those with normal experience may just skip rating,
while the raters with extreme ratings may be more likely to leave a review. So this is an example of participation bias. The average rating of the observed ratings in Hotel A and Hotel B is identical. But for the average rating of the true ratings, including the observed rating and the unobserved ratings, they're different. Well, Hotel A's rating is lower, Hotel B's rating is higher. So both Hotel A and Hotel B's observed rating is biased compared to their true ratings, and we want to mitigate this bias. Our model is quite simple. For a single item, we have n homogeneous raters and discrete ratings. Each rater's ratings follows the same underlying distribution P, and the ratings are independent. G is the participation probability, or we say the reporting probability of raters. So rater I will report his true rating with probability GXI. Otherwise, he will not report. So given the vector G, the rater's reporting probability only depends on his true ratings. Finally, we need an aggregator who takes the observed ratings as the input and outputs a single number. Without any restrictions on the reporting probability, in the worst case scenario, our G will be 0 for all rating R, and so no one reports. So we assume there is a known parameter Q indicates the lower bound of reportability for all rating R. We employ a robust aggregation paradigm and aim to find a robust aggregator F to estimate the expectation of true ratings. And our optimization goal is to minimize the regret relative to the ideal aggregator in the worst case scenario. Let me explain it. So X represents for the true ratings and X hat represents observed ratings. P is the underlying distribution and G is the reporting probability. This is the ideal aggregator who observes all the ratings, including the ratings they report or the ratings they do not report, and simply outputs the average. And mu is the expectation of the true ratings. This is the error of the ideal aggregator, and this is error of our aggregator. FQ is our aggregator with a known parameter Q. And this expectation is called regret, and we use the regret relative to the ideal aggregator. And we consider it in the worst case scenario, which means we consider the worst among all information structure, the pair P and G. So we use the relative regret so one can focus on the participation bias rather than, for example, error caused by high variance of P, which even the ideal aggregator cannot handle it. And our main challenge is we do not have any data from the non-participants. We do not have their history rating data or their rating data on other items, so we cannot learn their rating patterns. We consider this problem in two settings. When the sample size, i.e. the number of raters, n is known, the aggregator takes the histogram nu, n1 to nm as an input, where nu indicates the number of observed ratings, and nr counts the number of ratings of R for all R. Since we have assumed all raters are homogeneous, it is equivalent to take the whole observed rating x hat as input. And when the sample size n is unknown, we don't know the number of unobserved ratings, so the aggregator can only take the histogram n1 to am as an input. So when the sample size n is known, we propose the balanced extremes aggregator, BA for short. This picture illustrates how BA works. For the observed ratings, we know the count and we can calculate the mean. For the unobserved ratings, we still know the count, and the BA estimates the expectation of unobserved ratings is the convex combination of the extreme ratings, and the coefficient is alpha. It is the parameter depending on the observed ratings.
which is actually some kind of posterior. We'll talk about later in the techniques parts. So BA simply combines these two parts and outputs the results. This is the empirical results of BA. We tested BA with different N, M, and Q numerically. So the x-axis represents the lower bound of reporting probability Q, and the y-axis represents the logarithm gradient. There are actually 3 lines in each picture. The blue one is the simple averaging aggregator, which simply calculates the average of the observed ratings. The white one is our aggregator BEA, and the black one is the theoretically lower bound, which we established by constructing a special information structure. You can see the white line almost coincides with the black one, which means BA is almost optimal for a wide range of Q, and beats simple average aggregator, especially when Q is small. When the sample size N is unknown, we derive another aggregator called the polarizing averaging aggregator, PAA for short. And this picture illustrates how PAA works. So it takes the observed histogram as the input and creates two modified histogram from the original one. For the first histogram, it selects the threshold H1, KY, and only keeps Q fraction of the counts of ratings above K1. And for the second histogram, it selects the threshold H2 and only keeps Q fraction of the count below K2. And PAA then calculates the empirical mean for the modified histograms respectively and outputs the average. So PA, we have two theoretical results. When N goes to infinity, PA is optimal, and PA is near optimal in finite case. We also validate our aggregators on real-world data sites about the ratings of hotels. So the left column is a distribution of survey ratings, which are collected privately from the survey takers and considered to be their true ratings. Then the survey takers are invited to post their ratings as online reviews. Some do, some don't. So the online reviews, the right column is a distribution of online reviews, which are considered to be the observed ratings, which we use to test our aggregator. This table shows the results of aggregators. Here we set Q equals 0.3, which is a little smaller than the empirical average reporting probability. So the true empirical mean is 5.53, and all aggregators overestimate the average. Well, PAA is closer to the true empirical mean. BA has a higher regret than the simple average aggregator. So a possible reason is that ratings often exhibit smoother distribution in real world scenario, while BA designed to mitigate the impact of extreme ratings in the worst case scenario will not be well suited for distributions with ratings with smoother distributions. So in conclusion, next time you are trying to decide between two hotels with identical average rating as an online platform, if you want to secure a fair experience in the worst case scenario, maybe Hotel B is better. Okay, I think we have some time left, so I'll talk about some techniques. 2 minutes, okay. The design of BA is actually based on a special information structure we construct. And this is the information structure. Theta equals theta 1 or theta 2 is equal probability, and A is a parameter to be determined. So this picture illustrates how Richter I's rating is generated. So first, nature selects theta equals theta 1 or theta equals theta 2 with equal probability. If theta equals theta 1, then the rater's true rating could be 1 with probability A, otherwise it will be N. If the true rating is 1, then he will report his true rating with probability Q. If it is M, he will report surely. Theta 2 is metric. So BA is actually the expectation of true ratings given the observed rating X hat and the information structure theta. So if you can still remember how BA works, the alpha here is actually the posterior of theta equals theta 1, given the observed rating is X hat and information structure theta. As for PAA, the idea comes from analyzed in asymptotic cases. So when n goes to infinity, our optimization goal degenerates to this min-max problem, where the observed distribution B hat is proportional to the elements product of the underlying distribution P and the reporting distribution G. Since this is the quadratic function, the best aggregator F star will be the middle point of the minimum and the maximum of the optimization of the expectation. So by simple calculation, we can find the corresponding optimal G. It will be like this: is the threshold K1 and K2, which is exactly the thresholds in this picture. So what PA does is actually calculates the minimum and maximum and outputs the average. That's all. Thank you for attention. Any questions?
Thank you, Julian, for the nice presentation. Might be out. All right. Any question?
First, thank you for the amazing talk. It's very informative. And actually, I do have one question. So in your talk, you mentioned that you assume that there is some kind of like discount functions for the probability rating G. And you
Yeah.
don't assume, did you assume any structural properties for G? For example, the middle ratings will have less probability of being?
Actually, we test with some constraints like when I talk about the background, we talk maybe raters with extreme ratings has higher reporting probability, or we assume the G has some kind of Lipschitz consistency. But the conclusion remains the same. So I mean, the worst.
So I wonder if you have investigated a scenario when G is very biased, when, for example, as you quoted in the motivating example, when people tend to give rating when they have extremely bad and good experience, but in the middle ratings, they are less likely to rate.
Oh yes,
What happens to the estimator F when G is in this case?
So both BA and PA is actually designed for this scenario. The scenario will raters with extreme ratings has higher reporting probability. Is close to the worst case scenario for the sort of aggregator.
Okay, and what is the behavior of F in this case? For example, will F tend to push the two extreme ratings back to F?
Actually, F tends to be more conservative compared to the simple average. So if the simple average reports too high, it will lower. If the simple average reports lower ratings, it become higher.
Did you find a monotone structure of F? For example, if it's larger than the threshold, it will push it back to the middle, lower than the threshold?
It's not a threshold, so maybe it's we made the virtualization of our aggregator in the paper, but I don't have space in the pointwise. So it's actually you can imagine a line which is more smooth than the simple average aggregator. There is no evident threshold. It is in general more conservative.
Thank you. That answers my question.
We have time for one more very quick question. Anyone? All right, so just a quick question about the experimental setup. If you could explain a bit more the data set that you used. So I saw you have this ground truth rating. How do you go from there to the observe the ratings? Can you explain a bit more about the data you use?
The data set. So I can remove my point. So you're asking the data set I used in this paper or?
Yeah, for the experiments, right? You showed us.
Can remove my PowerPoint.
You can remove it.
Yes, can move it. It's stuck.
Wait, I think because of time.
Oh, briefly. So the data set is actually quoted from someone else's paper. So the experiments like this. So they send surveys to the people who stay at the hotel, semantic surveys, and these surveys are collected privately. So the survey ratings are considered to be the people's raters' true ratings. And then they invite some of the survey takers, randomly picked, to post their surveys on the online review as online reviews. So they are collected. They are considered to be the observed ratings. So we have the ground truth. So this when we do the experiment, it's very hard to construct or to obtain the ground truth. So this is the best data set we can.
Right. All right, let's thank our speaker again. Thank you. We have our next speaker on stage. Okay, so while we set up, the next paper in the session is titled Unlearning Incentives Learning Under Privacy Risks.
Okay, thanks for the introduction. Good afternoon, everyone. My name is Quan Wang, and I'm from Zhejiang University. It's a great honor to present our work titled Unlearning Incentives Learning Under Privacy Risk. This is a joint work with Renee Xu, Professor He, Professor Barry, and Professor Zhang. To begin, recent studies have highlighted that big data is a critical resource for the next generation applications. Deep learning is widely applied in areas such as smart home, smart city, and more data-driven personalized service. The data sharing creates a mutually beneficial scenario. Platforms can deliver more tailored service and users enjoy more relevant experience. However, evolving privacy regulations demand greater transparency in data handling. A central component of this regulatory push is the right to be forgotten, which allow users to request deletion of their shared data. In machine learning, this leads to the concept of unlearning, removing a user's contribution from a trained model without full retraining. Will unlearning provides a privacy-preserving mechanism. Its economic implications remain under explored. Platforms typically monetize user data through mechanisms like price discrimination and targeted advertising. Introduce unlearning may impose computational costs and affect platform model performance. At the first glance, this seems harmful for the platform profitability, but is that necessarily the case? This brings us to the first. Okay. This brings us to our central research topic. How does unlearning affect platform business model and economic outcomes? At the same time, despite the benefits of personalized service, many users remain hesitant to share their data due to the privacy concern, and they tend to be risk averse and privacy sensitive. We did a questionnaire survey by asking the user their willingness to share their data in 3 different scenarios. The results show that users are more willing to share their data when Unlearning is available. This leads to our first question. How can we quantify the impact of Unlearning on users' willingness to contribute to learning? To explore this, we began by modeling privacy leakage in data sharing. Each user holds private information such as their social or financial information. Each training sample is a noisy realization of this private information. Given the local training data, users then choose their local effort to reflect their willingness to share their data. The platform also holds some prior knowledge such as pre-trained model or information collected from other users. We quantify the privacy leakage using the conditional mutual information, and we introduce a parameter data to model the platform ability to exploit this privacy leakage. Importantly, before user upload their data, the actual leakage remain uncertain. Both the platform and the user lack the full knowledge of how their data will be used, or the correlation between the platform prior knowledge and the user's private information. Next, let's look at the interaction framework. It portrays in 3 stages. First, the platform offers a contract including 2 types of compensation: T for staying in learning and T hat for requesting and learning. Compensation may be monetary or in the forms of enhanced service. The user accepts the contract and then choose their local effort level. Later, after observing the realized leakage, the user decides to request Unlearning or not, and then the platform compensates the user accordingly. We define the ex-post utility for both the user and the platform. Users are risk averse, and their loss from the privacy leakage is scaled by privacy sensitivity parameter. Utilities also depend on users' Unlearning decision. When the Unlearning is triggered, this drops the platform revenue to 0 and incurs compensation T hat and Unlearning cost. This leads to the platform contract design problem. How to compensate for leakage while ensuring user participation and aligning user decision with platform objective. The contract must satisfy users intertemporal IR constraint and 2 forms of IC constraints. The challenge arises from the user's coupled decision. First, the local effort, and then whether to unlearn. The platform must jointly design T and T hat to maximize its surplus. To understand the incentive effect, we first examine the impact of Unlearning on users' willingness to participation, which helps explain our survey results. In practice, platform often offer fixed payments, and the user only decide whether to share their data. Theorem 1 shows that when Unlearning is enabled, the platform can reduce the compensation while still encouraging participation. Their Unlearning acts as an insurance, capping user potential privacy laws and increasing their expected utility. We now turn to a more general setting and observable efforts where the platform can monitor user behavior. Since Unlearning incurs cost, the platform must carefully balance the participation incentive with limiting the Unlearning request. This leads to our second key question: how can the platform incentive learning while properly electing a learning decision? To answer this, Session3 offers necessary conditions for optimal contract design. The optimal structure depends on user privacy sensitivity, the platform marginal revenue, and marginal learning costs. For highly privacy sensitive users, it's optimal to design T and T jointly to encourage the user to avoid learning. To avoid costly competition, for less sensitive users, the incentive structure differs. Importantly, Session3 shows that the optimal contract design problem can be point-wise decomposed by leakage level, making the contract design problem trackable. Building on this, we investigate the profitability and the different user performance, which led to our third key question: how do user risk aversion and privacy sensitivity affect the platform profitability when Unlearning is enabled? To answer this, we first analyze a binary leakage setting, high leakage level and low leakage level, where users' efforts shapes the likelihood of the high privacy leakage. This binary setting yields a closed form solution and deeper insights. Session3 identifies three cases based on the cost risk elasticity we defined, which capture how users' effort costs impact the likelihood of high privacy leakage. When privacy leakage sensitivity is high, Unlearning can increase platform surplus relative to scenario where it's not available. However, if the elasticity is low, user must exert much higher effort cost to share their data. In such cases, the Unlearning enabled platform may become less profitable due to the increased competition cost. We validate this theoretical insight through numerical simulation in a continuous leakage setting. The results are consistent, but notably, greater user risk aversion leads to a modest profitability gains. This is due to the highly risk averse users prefer smoother contracts, which improve the Unlearning enabled platform risk premium burden. Okay. In conclusion, we develop a model of uncertain privacy leakage with risk averse users, introduce a novel contract design framework incorporating Unlearning. Unlike prior work that focused purely on the monetary incentive, we highlight the incentive effect of Unlearning, which improves and demonstrate how Unlearning transforms the incentive landscape. Our results answer three fundamental questions and show that Unlearning can reduce the request competition, pass the way for the practical development of Unlearning. That concludes our work. Thanks for listening.
All right, thanks a lot, our speaker. We have time for a couple of questions.
Yeah, thanks for your presentation. And I have one question is that you have mentioned that Unlearning could actually could benefit the profitability of the business in the third question, right?
Third question. Yeah.
Yeah, so regarding the second point, I wondering if you have take the degradation of the performance of the model performance into account when you come to the conclusion of Unlearning could benefit the profitability.
Yeah. Although the unlearning rate will reduce the model performance, but it lower the platform compensation for the user's participation.
Lower what?
Lower the compensation for user participation.
Oh, okay, I see.
Yeah.
More questions? Thank you.
Thank you for the talk. I was curious, so you talk about like users' different privacy sensitivities, for example. It seems like there's, and this is pretty far beyond the scope of your work, so just curious if you have any like thoughts here. There's maybe a bit of a disconnect between like how we talk about privacy in like a technical sense, differential privacy, you know, whatever, and then like what a user maybe understands as privacy. And I was wondering, have you thought at all, or is there kind of work on how to communicate to users? Like, what is the privacy? Like, how should they think about setting their privacy settings? You know, how do you translate your like preferences into kind of a number or a knob you can turn?
There we assume the privacy leakage is realized after the user choose their efforts. In practice, for example, when you are in a shopping app, they have some personalized recommendation. The user may think they have privacy loss.
So then I guess in like a personalized shopping app or something, kind of what is the choice that is like given to the user? What do they kind of decide? Is it using the app or not? Or is it some knob they get within the app about levels of personalization?
Sorry,
Oh, sorry. Like, yeah, like what, you know, you talk like so the user chooses this effort, I guess in your kind of shopping app example, what does that translate to in that example?
Sorry,
Oh, no worries. Sorry. Maybe I'll follow up after with this question.
Okay, thanks.
All right, we run out of time for questions, so let's thank our speaker again. If we can have our next speaker on stage. So the third paper in the session, try to set it up, is titled Relying on the Metrics of Evaluated Agents, and will be presented by Serena Wang.
Okay, thank you so much. I am, as you said, presenting work on relying on the metrics of evaluated agents, and this is joint work with Mike Jordan, Katrina Leggett, and Preston McAfee, and Katrina and Preston are in the audience here as well. So in this talk, we're going to be focusing on metrics, which are at the core of online platforms, business operations, AI development and evaluation. And when I say metric for the next 12 minutes or so, I mean a quantitative indicator of the value or difficulty of some task, which often determines an agent's reward. So, for example, say like in business operations, a metric could be the number of lines of code written by a software engineer, or maybe the number of NeurIPS papers published by a researcher. With online platforms, you could have metrics like the delivery times for some like food delivery platform, or click-through rates for video recommendations. And in AI development and evaluation, maybe you're familiar with the MMLU score for LLM, like multiple choice question answering capabilities. Or more recently, there's this like AI Illuminate AI safety score from ML Commons. So anybody who's like familiar with these settings knows that none of these metrics really tell the whole story, right? We know that the number of NeurIPS papers published by a researcher is like far from a perfect indicator for your research impact. It really should be the number of www papers instead, obviously. And yet metrics are still so central to decision-making in these systems. So the fundamental information problem that we're interested in this work is this problem that's faced by evaluators, where really the hard question isn't so much how do you collect or process data, but more what metrics should we be collecting in the first place? And we think of this first issue as one of dealing with, say, known unknowns, but the problem we're really trying to capture in this work is to think about unknown unknowns here. So as an example from the AI evaluation space, you have like currently regulators are able to mandate the collection of metrics for AI systems, but fundamentally they face this problem of, well, they don't know how to measure, say, risk or safety or harms or things like that. So maybe the information might not be held by the regulators themselves, or maybe you have some issue of unknown unknowns, but a potential solution that we are exploring here is that, well, maybe that information lives somewhere else in the system. Like maybe the evaluated agent has better information about how to measure their own performance. And so the question that we focus on is, well, when would an agent then prefer to share these metrics that are previously unknown unknowns for an evaluator? And our main contribution here is a theoretical model of incentives for an agent to share these kinds of unknown metrics with an evaluator. So before I get into the theorems here, I want to just build some intuition for what we're doing with a quick thought exercise. So imagine you're a food delivery courier, and the app offers a price for each delivery that you make based on its features. So this is like some app that you're working with. So I want you to raise your hand for the following features. Which features would you want or not want the pricing algorithm to account for? Okay, so raise your hand if you want the algorithm to account for whether the restaurant tends to have a super long wait time. Okay, raise your hand if you want the app to account for whether it's raining outside. Cool. Okay, finally, raise your hand if you want the app the pricing algorithm to account for whether the recipient is likely to tip generously. Interesting. Okay, we got some hands. So looking at the distribution of hands across the room, this is probably where I would have raised my hand here. And this kind of gives an intuition for what our theory as a preview shows that an agent is going to prefer to reveal metrics that differentiate the highest cost settings from the rest and conceal metrics that differentiate the lowest cost settings from the rest. Okay, so let's get into the model for this. We start with a standard agency game here, where we think of the principal as, say, the rideshare app, and the agent as a driver. And let's say that the principal and the agent have a shared prior over the agent's cost for completing the ride. So that's this variable C. So in this standard setup, you start with the principal goes first, offering a payment to the agent for completing the ride. And the agent, upon observing their cost C, exerts effort and completes the ride if that cost is less than the payment that was offered, right? And if they exert their effort, then the principal achieves value B. So what we add to this model is the ability for the agent to have some cost, to know of some cost correlated variable, let's say the traffic amount, X, which the principal is not aware of and not currently including in their pricing mechanism. So what we add is one step of information transfer before the rest of the contracting game, where the agent has the opportunity to reveal the observability of this variable to the principal. And if they do so, then this variable X now gets factored into the payment algorithm, row of X here, and the agent exerts effort if their cost is less than this row of X. So the question then that we ask is, okay, well, when does the agent prefer to reveal X in this first step of the game? So there's kind of two competing effects here, right? So on one hand, if the agent reveals this metric at the beginning, then they will complete more rides more often because they'll have higher compensation in the higher cost settings, right? So here, when there's high traffic, they're gonna get paid more. On the other hand, if they were to conceal this metric, they will get paid more for the lower cost settings, right? So they'll be able to extract more information rent. And so you have these conflicting pieces, which make it not so obvious whether for a given variable, the agent actually prefers to reveal this if it's an unknown to the principal. So this brings us back to our theory that we established in the intuitive example we had earlier, where we're going to show that the agents prefer to reveal metrics that strongly differentiate the highest cost settings from the rest and conceal metrics that strongly differentiate the lowest cost settings from the rest. So let's formalize this. Let's define a thresholding feature, xt, to be a binary variable, which is 0 if the cost is greater than some threshold t, and 1 if the cost is less than or equal to some threshold t. So you can think of this as just perfectly telling you if you have, some high or low cost, depending on where the threshold t is. So the this is the main theorem that I'm going to show today is under some regularity assumptions, and if the cost is bounded, and if the principal's value is within some range, and which we're going to talk about in a second, then there exists some threshold t lower, such that for all thresholds t greater than t lower, the agent is going to prefer to reveal the thresholding feature xt. So you can think of this as, okay, under these kind of general conditions, under this broad set of conditions, now for high enough thresholds t, the agent will always prefer to reveal such a feature. Okay, so kind of the most maybe non-trivial or maybe restrictive condition in this theorem is this condition on the principal's value here, which says that the principal's value has to be within some range. And I have these Goldilocks and the three bears analogy here, where if the principal's value b is way too high, you can think of this as oh, the app gets $1 million from a given ride. Then the principal's optimal hidden price will already be the maximum cost that the agent could have. And so the agent can only end up with lower prices from revealing more information. On the other hand, if the principal's value is too low, then the principal just won't price high enough to accommodate the highest cost agents even after information is revealed. And so we have that for B in this sweet spot in between, this very general intuitive property holds of the agent wanting to reveal features that indicate high cost. Okay, so we've now talked about some results in the case where so far we've only allowed the agent a sort of restrictive action space, right? The agent can only either reveal or conceal the feature X. But to kind of get a broader understanding of the agent's incentives in these cases, we also relax this and expand the agent's action space to allow them to, say, reveal garbled information. So let's say that instead of just only getting to pick whether to reveal or conceal, the agent can reveal some garbled variable y, which is x with probability epsilon, and some uncorrelated random variable psi with probability 1 minus epsilon. So this is this model just interpolates between the full revelation and full concealment settings, where if epsilon is 1, then you have full revelation. If epsilon is 0, then you have full concealment. So there's two really cool insights that I'm going to share with you today about this garbling setting kind of gives us. And that is that both of the following settings exist. So the first setting is one in which the agent prefers some amount of garbling over full revelation over full concealment. And the second setting is when the agent prefers some amount of garbling over full concealment over full revelation. So let's get into why exactly each of these settings is interesting. So the first setting is interesting, to me at least, because it shows that, okay, in this model, there's some economic value to privacy here, to adding noise to the agent's information, where the agent is deriving some utility from adding noise to their data compared to fully revealing that information. So in this model now, we have that even without any inherent value for privacy on the agent's part, they still prefer the privatized setting. The second setting I actually think is even less intuitive in some sense and maybe more interesting from a policy standpoint, where in the second setting, what you have is that the agent prefers to reveal some amount of garbled noise, but some amount of garbling information. They prefer that over fully concealing the information, and they prefer concealing over full revelation. So this is a case where if the agent didn't have the opportunity to garble, if they were stuck in that binary case, they would have kept the information hidden. But once this garbling mechanism exists and the principal is willing to commit to maintaining that level of garbling, the agent actually will reveal more information in the system and more information comes out here, and you actually have Pareto improvement here, where allowing for garbling results in strict Pareto improvement for both the principal and the agent, and both benefit in this sense from the option of privacy. Okay, so I'm going to kind of, oh, great. Okay, so I'm going to wrap up here by kind of zooming out a bit to give a bit of motivation for what other problems the three or four of us are thinking about. So I've given kind of a toy model, or not so much, but like a very stripped down model so far. But in AI, we're already relying on the metrics of evaluated agents and all sorts of other interested parties like throughout these environments. For example, the US AI Safety Institute is like partnering with Anthropic and OpenAI to develop AI safety evaluations. You also have like setups like Chatbot Arena, where this is like a community-driven evaluation where people can just submit prompts to be part of the evaluation set. And so in these settings, you have many of these kinds of distributions of information and unknown unknowns flying around everywhere. So what we're really trying to model here is like capture what happens when you have these unknown unknowns that are affecting people's choices of what to report and utilities around these things. And I know I'm probably like preaching to the choir here when I say that like, evaluation is really not a static problem. It's really a dynamic multiplayer game across all of these settings with all of these different actors that have different information. And so some of the takeaways from this work in like thinking about this wider game is where we show that maybe sometimes an agent will be willing to reveal an unknown metric to the evaluator, depending on the properties of that metric. But there's like, a lot of open questions here to thinking about unknown unknowns in these settings, which is, well, one, like what if a principal can pay for information, or what about competition between agents? So, I think any of the three of us who are here would be happy to talk more about any of these kinds of open directions. Thank you so much. And yeah, happy to take questions after.
Right, thanks for the great talk. We have time for a couple of questions. Any question?
Thank you for the talk. I really liked it. I liked your example, and I think I'm actually hoping that you can just go over one of your examples in a little more like a little slower, a little more detail. I think I got a little confused at when you talk about cost, like is that like the cost to the principal, or maybe like the agent's notion of like cost? Can you go through your like food delivery driver like example again and say the kind of like when the cost is like giving information about high cost or low cost, like how that relates to the three options that you had?
Oh yeah, you mean like this part?
Yeah, or like you had the like, is it raining?
Oh, sure. Yeah. Okay.
How that relates to kind of the rest of the talk that you had.
You can leave
Yeah.
that. It's fine.
Okay, great question. Thank you. So I was actually, when I was constructing this example, I was trying to think of cases where these kind of reflect that like threshold feature XT. So think of A as like, okay, here's if you just have an indicator that's whether the restaurant tends to have a super long wait time, then this is something that indicates basically if it's one, okay, it's one if like you as the courier are going to have to wait like for a really long time, and so that's like high cost to you because time is money in this sense. But otherwise, if it's not one, it's like giving no information the rest of the time, or no information, and that you can still get a prior over what happens when it's zero, right? On the other hand, like with C, I was trying to come up with an example where here's an indicator of when you're going to have low cost, in that if if the recipient is going to tip generously, then maybe this already makes up for like the gas cost that you incur and everything like that. So you'd be willing to take the job regardless of what the principal offers. Yeah, thanks for the question.
Any other question? Sure.
I guess this is just kind of clarification. In economics, sometimes they talk about cherry picking and lemon dropping. So cherry picking is you're picking the best things, and cherry dropping is you're kind of getting rid of the worst things. Is that's kind of what's happening here, that you want to allow people to cherry pick, but you don't want to allow them to lemon drop?
You mean like on the principal side? Like,
Well, like it seems like when the threshold is high, then you're kind of allowing people to cherry pick, and when the threshold's low, you're allowing them to lemon drop. So it's kind of saying that they'll reveal cherry picking information, but I'm not lemon dropping information. Am I understanding that correctly? Kind of.
Sounds right to me. I don't know, Preston or Katrina, do you have any comments on anything to add to that?
Yeah, except that I think it's backwards because it's a cost. So that is to say, it's a cherry when it's a low cost, it's a lemon when it's a high cost. But otherwise, I think it's, yeah, it's the same, it's similar, it's language for the same ideas.
All right, I think we run out of time, so let's thank our speaker again. All right, now, do we have the speaker of the fourth paper in the session in the room? The paper is titled Navigating the Deployment Dilemma and the Innovation Paradox, Open Source versus Closed Source Models. Do we have the speaker in the room? All right, so now we have two options. What I would do is now wait to be synchronized with all the other sessions before we move to the last paper in the session. However, I understand if I do that and now we have 12 minutes of nothing, people are gonna leave and not come back. So since we have quite a few people in the room, I'm gonna ask the last presenter in the session to come on stage, and we're gonna move to the last paper in the session against the rules. So we are not synchronized anymore. So our next paper is going to be presented by Yichen, and is titled Query Design for Crowdsourced Clustering, Effect of Cognitive Overload and Contextual Bias.
Thanks for the introduction. Hi, everyone. My name is Yichen. I'm a third-year PhD student at the University of Wisconsin-Madison, and I will be presenting a work Query Design for Crowdsourced Clustering, Effect of Cognitive Overload and Contextual Bias. So the title of our work has three concepts: crowdsourced clustering, cognitive overload, and contextual bias. So I will first discuss the motivation of crowdsourcing, and then I will describe what cognitive overload and contextual biases are. So why do we need crowdsourcing? This is because supervised learning, especially deep learning, require a lot of labeled data. For example, ImageNet contains millions of labeled images, and it played an important role in advances of object recognition. And due to the large quantities, it is impossible for researchers to label these data themselves. So instead, it is collected by hiring other people to get annotations. And moreover, in the current era of foundation model, fine-tuning and alignment also require good quality label data. Now, what is crowdsourced clustering? Crowdsourced clustering or crowd clustering uses human input to group items into meaningful clusters. For example, consider you have a set of dog images and you want to label them by their breeds. One way to do this is to ask crowd workers to label the dog images directly according to your breed. But they are not domain experts, so it is very hard for them to accurately identify the breed of each dog. So like answering the question like, what is the breed of this dog is almost impossible. But what they can do is to compare and distinguish between two dogs. For example, by noticing differences in size, color, or fur texture. This is a much simpler task and doesn't require any special knowledge about dogs. So by treating each dog image as a node in your graph and drawing an edge between two nodes, if the corresponding dogs are judged to belong to the same breed, we can construct a similarity graph. We can then apply a graph clustering algorithm on the adjacency matrix induced by this graph, allowing us to group the images into clusters, and we can assign labels at the cluster level to effectively generate a label dataset. Note that due to budget constraint, it is not possible to fill in all the entries of this adjacency matrix. Additionally, since the crowd workers are not experts, they could still make some errors in judging similarity. So we have to cluster a partially observed noisy graph. For clustering to work well, two things matter: the quantity and the quality of the entries in the matrix filled by the crowd workers directly affect the performance of clustering. Here, quantity refers to the total number of entries filled under a given budget, and quality refers to the amount of noise at each entry. That is, the 0 becomes a 1 and 1 becomes a 0. So the question is, how should we design the queries to fill in the entries of the adjacency matrix? Previous work has shown that presenting 3 items at a time allows us to fill more entries in the adjacency matrix with higher quality under the same budget, which in turn induces a better clustering performance compared to presenting a pair of images at a time. So naturally, this raises the next question: what if we go further and ask for 4, 5, or even 6 items at a time? This leads to the problem of cognitive overload. While showing more items at once might allow us to fill more entries in the adjacency matrix, having a lot of items in a query might also be overwhelming, which may degrade the quality of entries that are filled. We wonder if we are going to observe something like this, that is, as the number of items increases, the performance also increases, or something else. We use 2 datasets in our experiments. First is the dog3 dataset that contains 3 different breeds of dogs, shown here, and these dogs are taken from the Stanford dogs dataset. The second is birds5 dataset, which contains 5 bird species and with some outliers. So there are about 342 images in total, and the birds are taken from the Caltech UCSD birds dataset. We conducted all of our experiments on Amazon Mechanical Turk, and to evaluate the effect of cognitive overload, we vary the number of images per query from m equals to 2 to m equals to 8. To ensure a fair comparison across conditions and balance the workload in terms of time, we fixed the total number of images shown in each set of queries to approximately 60, in order to ensure that the overall time is the same for each survey. Here is the instruction we present to the crowd workers. We show this instruction at the top of each query. And here's the user interface that we used. Crowd workers are able to drag and drop the images from ungroup section to group sections to form clusters like this. So here are the results of the clustering performance on the effect of cognitive overload. We use variation of information, or VI, and information theoretic measure to measure the clustering performance. The lower the VI, the better the performance is. So as we mentioned before, having more images per query means that we fill more entries in the adjacency matrix. If filling more entries, then we would expect the VI to drop continuously. That is, we expect something like this. However, we did not. We can see that for dog3 and birds5 dataset, VI decreases initially and reaches its minimum when m is 4. Then we begin to experience diminishing returns, especially in the dog3 dataset. So this result shows that we cannot blindly add more images to a query and expect the clustering performance to increase continuously. It will backfire. So now we turn our attention into the effect of contextual bias. Contextual bias is the idea that even if 2 queries have the same ground truth, for example, 3 birds belong to 3 different species, the specific species presented in each query might influence how crowd workers respond. How does the context, the actual items shown, affect their judgment? Now I will describe how we designed the experiment to show the effect of contextual bias. In this experiment, each query involves 3 images of different bird species, 2 of which are least term and arctic term, and we vary the 3rd image in order to see what are the chances that the 2 terms are clustered together given 3 different contexts. So in experiment 1, we show 3 terms, which look very similar to one another. In experiment 2, we replace the common term with an albatross, still somewhat similar, but with more noticeable differences. In experiment 3, we substitute a cardinal, which differs drastically in color and appearance from the terns. All 3 experiments share the same ground truth. The 3 birds belong to 3 different species. However, we designed these experiments to examine whether crowd workers' responses changes depending on the specific birds shown. We want to see what are the chances that the 2 terns are getting clustered together when we vary the 3rd image. Here, the numbers shown are the probability that the 2 terns are clustered together. Indeed, as we can see, when the 3rd image becomes less visually similar to the least term and arctic term, the probability that the 2 terms are clustered together given the 3rd image increases. This demonstrates that the noise in the crowd responses is influenced by the specific items presented in each query, that is, by the context. So in conclusion, in crowd clustering, showing more items per query initially improves the clustering performance. However, the benefit diminishes after 4 items per query. Moreover, when you present more than 2 items per query, the noise in the answer becomes a function of the context of the query. So when designing surveys to collect data, it is important to take cognitive overload and contextual bias into account. Thank you.
Thanks. Any question?
Thank you for the talk. I'm curious, so maybe another effect that you could imagine, like also accounting for, some of the effects you saw for contextual bias is like whether people want to make one large group of all the birds or whether they think like, oh, I should have at least 2 groups in this category, like from these birds. Did you look at like, are people biased towards like do they put all of the birds together in one group as often as they should, or is there some bias towards having more or fewer groups?
I think so. Based on what I observed, people tend to group the most similar pairs of birds together, and I also have a table in the paper that shows the probability that like what all possible answers. So maybe I can't remember numbers right now, but maybe you can refer to that table. And
Thank you.
Yeah.
Any other question? I'll ask you a question.
Yeah.
So in a crowdsourcing setting, you need to give a monetary reward to the crowd workers who complete the tasks. You know, if you think having 2 images or more images to group, I would imagine the reward should increase if you have more images. So did you consider the cost implication of increasing the number of images to cluster with the information you are collecting to having multiple images? The task.
So when we varied m from 2 to m to 2 to 8, we fixed the total number of images shown in a set of queries. So for example, when m is 2, we show like 30 queries. So like in total there are 60. And when m is 3, we show 20 queries. So like we'll keep the total number of images same. So the budget, like or the price we pay for crowd workers is also same. Yeah,
thanks. Any other question? All right. If not, let's thank our speaker again. Yes. And this concludes the session because we didn't have the 4th speaker in the session. Thanks all.
So you look up, I know last year you can show there are also I also in Chinese. So I was the name. That's about. Go up and it's This is not like, it's why I know that from being something.
And that's the idea. Like some confidence that you have shown that even actually, it's like instead of, yeah.